Good afternoon, everybody. I am Vishwa Bandhu Singh. I am from Department of Geography, Punjab University, Chandigarh. And today we will be talking about information extraction from satellite imageries. So before coming to the process of information extraction, let us quickly talk about the remote sensing process. Now, remote sensing is usually considered as the science of identifying, observing, and measuring objects without coming into any physical contact with them. And this kind of process usually involves the detection and measurement of different wavelengths, which are either reflected or emitted by various surfaces. For example, in case of Earth system, sun is the prime source of energy, and it reflects energy of various wavelengths. And the process involves the detection, identification, and classification of spectral responses by various surfaces. Remote sensing usually considered as the science and to some extent as an art of acquiring information. Now we call it as a science because it is based on certain fundamental principles from the physics, that is radiation principles. But at the same time, this process requires a lot of expertise, skills, as well as creativity of the observer or the analyst, because given a condition, different people, depending upon their expertise, they will interpret a satellite image showing the similar spectral responses in a different way. So that is why extracting information is part of the art of acquiring information. Okay. So now, just by looking at these two images, we can easily identify, we can measure the extent of damage that has taken place in this area. So this is one of the basic application of remote sensing, that it helps you in comparing various time periods with respect to the features observed on the surface. Now, these are different images pertaining to different spatial resolution. We have one satellite image covering entire India. Then we have one image representing the southernmost part of India and Sri Lanka. And then we have the third image pertaining to a very small location. And in this case, this image pertains to Chandigarh city. Now, these different satellite images are on different spatial resolution, and they give information of different levels. For example, in case of India, we can extract from this image, we can extract the minimum amount of information, but that information pertains to a very large area. In the second image, you can see India and Sri Lanka, and in between we can also see a small connection between both the countries. In this case, the level of information has increased, but the size of the area has decreased. And in the third image, we can see the entire city and its surrounding. The level of information has increased. We can extract a larger amount of data, but for a very smaller area. So these are a few examples of different scales at which satellite images provides us information, and different levels on which we can extract information. These are some of the most recent high resolution imageries. Nowadays, with the help of these high resolution images, it is possible to even extract information at household level. For individual houses can be identified, and representation can be done into 3 dimensions also. This process has now capabilities of giving us information at a very micro level. So now let us talk about satellite images, what satellite images are and what are their characteristics. Now, a satellite image usually is a two-dimensional representation of reality. Now, these satellite images, they are either pertain to the entire Earth surface or some part of it. And depending upon how these satellite images are acquired, we usually divide them into two different types. One is known as the photographic or analog image. Another are the digital images. But our today's lecture, we will focus on just the digital images. Now, digital images consist of different rows and columns. The rows and columns are divided into a smaller spatial unit known as pixel or the picture element. Now, these pictures or picture elements, they represent the amount of energy which is reflected by the surface. And depending upon how many wavelengths we are using, we divide these digital images into three parts, which are known as multispectral images, superspectral images, and hyperspectral images. Multispectral images are all those images which contains at least two spectral bands or more, whereas in case of superspectral images, we have a higher number of spectral bands used for acquiring a satellite images. For example, we can have 20 different spectral bands used in acquiring a satellite image. We'll call it a superspectral images. Then we have hyperspectral images. As its name suggests, it has even the higher number of wavelengths used for acquiring the satellite images. The difference between superspectral and hyperspectral images are that in hyperspectral images, the spectral bands, they represents the continuous wavelengths, which means that there is in between, there is no break in the wavelength. Whereas in case of superspectral images, we can have breaks in wavelengths. Now, we can differentiate between these three types of satellite images using this small diagram. The first, the topmost diagram, we have spectral width ranging from roughly about 0.4 micrometers to about 100 micrometers. And the same spectral wavelength, we have taken 6 wavelengths, 6 divisions of the entire range. So in this case, we have 6 satellite images taken for the same area. So in this case, we will call it a multispectral image. In the middle diagram, the same wavelength we have then further divided into about 10 to 12 different wavelengths for the same. In this case, this is representing the superspectral. The last part we see, we have a very small size of wavelength. That width is very small. Even for example, between 0.5 to 0.7 micrometers, where we had captured 3 different images in the multispectral. Here now we have divided these smaller wavelengths into even smaller sized wavelengths. So in this case, we have more than 50 or 60 different satellite images captured within the same wavelength width. So in this case, it becomes the multispectral image. Satellite image, you see in this we have given a picture. On one side you see there are different shades of gray between pure white to pure black, and for the same pixels we have some digital numbers. Okay. So satellite images actually store the information in terms of these digital numbers. These digital numbers are representing the amount of energy which is reflected by that particular surface. So here you see there are certain values where 0 is written. Now 0 refers to that particular area which is not reflecting any energy, which means that it is absorbing almost entire energy. On the other hand, the higher numbers, for example 255, 238, these values are representing those areas which are reflecting the higher amount of energy. And in case of different shades of gray, all the zero values are represented with pure black, whereas values with 255 or higher numbers, they are represented with white pixels. Okay. Now, so therefore these pixels, they are actually the reflectance values of that particular area. Now you see these are four different images. Each image is taken in a different wavelength. So first band 1, the blue band, it represents the image taken in 0.4 micrometer to 0.5 micrometer wavelength. Band 2, the green band, represents the wavelength used from 0.5 micrometers to 0.6 micrometers. Band 3 represents 0.6 to 0.7 micrometers. So the first three bands, band 1, 2 and 3, they are representing satellite images taken in the visible spectrum. This is the spectrum within which human eye can see. The fourth band represents the infrared part. This band, this energy we cannot see. Okay. This pertains to 0.7 to roughly about 0.9 micrometer. So we have four different satellite images taken into four different wavelengths, and therefore these are multispectral images. Now all these images, they will appear in different shades of gray only, because in order to view color, human eye require combination of three different bands, say blue, green and red, the primary colors, and when we combine them, only then we are capable of viewing colors. Okay. So basically individual bands, they gives you the black and white satellite images, and only when we fuse them together we get the color composite. Now this is again another example of three different bands used. So we have green, red and near infrared bands. Okay, which means that we have taken two satellite images, green and red band, from the visible spectrum, and near infrared part, which our eye cannot detect. Now if you look at these three images, you will find that they pertains to the same area. They are representing the same features, but the way these features are appearing in satellite images, it is varying from one image to another image. Particularly in near infrared, you can see the most brightest part is appearing in darker shade in green and red band, which means that if the same surface, it will behave differently in different spectral wavelengths. Okay. That is why we capture a satellite image in different wavelengths. Okay. If an object is appearing same, let's say in two different bands, but it is appearing different in third band, we are able to identify that objects are different from each other. Okay. Now the lower picture, it is representing the color composite. Now in this case, you see we have a bright red patch in the center, okay, surrounded by different shades of blue. Okay. So this is representing a surface surrounded by a water body, and in this case the red colors, they are representing the vegetation. Okay. Since we are using green, red and infrared part, now vegetation is appearing red because vegetation has the maximum reflectance in near infrared. Okay. Therefore in any satellite images where we have used three different bands, and one of the band consists of infrared part, in that case any vegetation cover, it will appear in red color. So again we have two different images. One is the normal color, the true color composite, and the same area is represented by the false color composite. You can see in the false color composite, it is quite easy to demarcate the boundary of vegetation cover, which is slightly difficult in normal color composite. So therefore, whenever analysis of vegetation is concerned, we usually take into consideration the near infrared wavelengths. Now, another important aspect of satellite image extraction is to know the different resolutions pertaining to a satellite images. A resolution usually defined as the measure of the ability of a device or a sensor to differentiate a value. Higher resolution will give us the finer details. But in case of satellite images, we have different types of resolutions. Usually, when we talk about resolution, we are, for example, let's say in case of our mobile phones, usually we talk about resolution in terms of its capability of giving us the clearer picture. But in case of satellite images, we have different types of resolutions. These are spectral resolution, radiometric resolution, spatial resolution, and temporal resolution. Spectral resolution refers to the number of wavelengths which are used to capture a satellite images. So for example, in case of a multispectral image, we can have 4, 5, 6 different wavelength bands used to capture satellite images. So in that case, the spectral resolution will be 4, 5, or 6. Whereas radiometric resolution refers to the sensor's capability to identify various uh, gray shades ranging between pure black and pure white. So in this case, higher the number of levels which a sensor can identify, better will be the resolution. Now this kind of resolution is usually measured in terms of bit. So 1 bit resolution is equal to 2 raised to the power 1, which is equal to 2. So which means that in case of 1 bit radiometric resolution, the sensor will be capable of identifying just 2 different shades of gray. That is, either it will be pure white or it will be a pure black. So in such case, it is very difficult to identify features if they have a lesser number of gray shades. Whereas in case of, let's say, 8-bit data, that is 2 raised to the power 8, that is equal to roughly about 256 shades. So higher the number of shades identifiable by the surface, more easier to identify or differentiate between similar looking objects. Okay. In case of lower radiometric resolution, two objects which are almost similar but they are not same, they will appear in same shade in low radiometric resolution images. But in case of higher radiometric resolution, differentiation between these similar looking objects can also be made. Then third type of resolution is spatial resolution. Spatial resolution refers to the sensor's capability to distinguish the smallest size of object which can be identified on a satellite image. Now, in this resolution, it is defined usually in terms of units of kilometer or meters. For example, a spatial resolution of 100 meters means that any object which has dimensions of 100 meter by 100 meter, any object which is larger than 100 meter will be identifiable, whereas any object which is which has the size less than 100 meter, it cannot be identified on a 100-meter resolution satellite images. So in this case, spatial resolution, smaller the number of spatial resolution, say 5 meter or 1 meter, it will give us the better interpretation, because in case of 1 meter spatial resolution, we will be able to identify very small size object. Okay. So in case of spatial resolution, as the size of pixel reduces, the capability of data to interpret objects, it also increases. Then we have temporal resolution. Temporal resolution refers to the time interval taken to acquire satellite images for the same area. Now, in case of remote sensing satellites, These are near pole to pole orbiting satellites, which means that they rotate from near pole to pole direction. Okay. And once that one orbit is over, and by the time satellite comes back to its previous position, Earth moves from its own place. So in that case, the satellite captures the adjoining part of the earlier tracked area. So in this case, a satellite takes few days to come back to the same place. So the time interval for acquiring satellite image of the same area is known as the temporal resolution, and this temporal resolution varies from satellite to satellite. Usually Indian satellites, IRS series satellites, medium resolution satellites, they have temporal resolution of 10 to 15 days. Means that the same area is covered after the interval of 10 days or 15 days. Now this is one of the example giving us information about the spatial resolution. So we have different satellite images pertaining to the same area at different spatial resolution. So on top we have spatial resolution of 0.5 meter by 0.5 meter, and we have maximum spatial resolution of 80 meter by 80 meter. Now you see, as the size of pixel is increasing, the availability or the amount of information which we can extract from the satellite images is also decreasing. So at 0.5 meter by 0.5 meter resolution, we are capable of seeing roads, houses, trees. They can be individually identified and demarcated. But at 80 meter resolution, you see, we are hardly able to see any of these objects. Whereas in case of, let's say, 10 meter by 10 meter, we can just see the outlines. We can identify that this particular surface may be a road or maybe a building, but we are not able to exactly demarcate the boundaries of these surfaces. So you see, as the size of pixel decreases, the availability of information, it also increases. So spatial resolution is one of the most important characteristics of any satellite images, and our capabilities of extracting information rely hugely on the spatial resolution. However, the other type of resolutions, spectral and radiometric resolutions, they are equally important, because extracting information from a digital satellite image also requires the understanding of the radiometric as well as the spectral behavior of the surfaces. Now, how do we identify different objects or surfaces? Now, in order to do that, we need to understand the behavior of surfaces with respect to incoming solar radiation. See, remote sensing is nothing but understanding of the reflectance behavior or the absorption behavior of different surfaces. Now, in this case, spectral signatures are very important. Now, these spectral signatures refers to the unique characteristics of any surface with respect to reflectance of energy and its absorption. Okay. Any surface, depending upon its physical and chemical property, react differently to incoming solar radiation. Now, by analyzing these spectral signatures, we can identify various surfaces, various features, and we can differentiate between similar looking surfaces based on their reflectance behavior. And in order to make things easier, we also draw certain curves with respect to the reflectance behavior of surfaces, and therefore they are the graphical representation of these spectral signatures is known as the spectral reflectivity curve. Now, in case of spectral reflectivity curve, we plot the reflectance values of different surfaces at different wavelengths, and by doing so, we are able to draw a curve for a particular surface, and based on that curve we are able to identify that how a particular surface, for example water, behave differently at different spectral wavelengths. Now from a satellite images we can extract information about four major surfaces. Okay. These are vegetation, water, snow and soil. Now by understanding the spectral behavior, how these surfaces behave with respect to different wavelengths of incoming radiation, we can draw certain average behavioral characteristics of these surfaces. So let us start with the vegetation, that how vegetation is identifiable using these spectral signature. Now vegetation, the spectral signature or how a vegetation will behave, it depends on three important factors. One is the pigmentation, another is the physiological structure of the leaves, and the moisture content in the leaf. Okay. These three factors they influence the spectral responses of any vegetation. So from this graph you see we have on x-axis we have reflectance values, that is how a vegetation reflects, and on x-axis we have different wavelengths measured in micrometers. So we have different wavelengths ranging from visible spectrum to near infrared to shortwave infrared. Okay. And the curve is representing the behavior of vegetation. So you see in the visible spectrum, that is 0.4 micrometers to about 0.7 micrometers, you see the curve is very low. And in case of blue band and green red band, we see the reflectance is even very less, whereas in case of green we have slightly a upward curved surface. So now this is the reason here within the visible spectrum you see green part is reflecting the maximum energy, and it is due to this reason we see any vegetation in green color, which means that any vegetation, a tree or a plant, it absorbs higher amount of blue and red energy, whereas it reflects more of green energy. That is why any vegetation is, it appears green to us. But if you look at the curve ahead in the near infrared part, you see the reflectance increases manifold. You see we have more than 40 to 50% reflectance of vegetation in near infrared part. Okay. Which means that vegetation reflects highest energy in near infrared, but since we cannot see this energy, we just see any vegetation in the green color. And then in the short wave infrared you see again the curve, it starts moving downward, and in between we have a strong dip in this curve. These dips, they are representing the absorption of energy. So in this case the moisture content influences the reflectance behavior, which means higher moisture content will absorb more of energy. Okay. So that is why near infrared wavelength is most suitable wavelength as far as analysis or interpretation of vegetation is concerned. You see we have drawn different curves for vegetation, and you see these curves, they are representing the reflectance behavior depending upon the moisture content. So we see as the moisture content is increasing, the reflectance behaviors are changing and surface is reflecting less and less amount of energy, which means that higher the water content in tree leaves or in vegetation, it will absorb more energy and it will reflect less amount of energy. And depending upon our understanding of this relationship, we are also capable of identifying the stage at which that vegetation is, whether the vegetation is perfectly healthy, or it is moving towards the more mature stage. The other factor which affects the reflectance behavior of vegetation are the effect of vegetation senescence, effect of phenology, and effect of canopy geometry. Now these relates with the aging. For example, vegetation senescence refers to the aging of vegetation. As vegetation matures, let's say the wheat cultivated area. Initially, when the wheat crop is growing, it will reflect high amount of energy. Its spectral appearance will be different. Okay, but as it will mature before harvesting, it turns into brown or dark brown color, which means that now the vegetation is maturing and the moisture content is becoming less and less, and it will appear differently. So by analyzing this changing moisture content, we can identify the stage at which that particular crop is. And this kind of understanding is very important when we try to estimate the crop production. This kind of information is also important when we are trying to find out those areas where vegetation is being affected by any kind of disease. Because if a vegetation is being affected by a disease, its spectral responses, it will change. And by comparing the changed spectral responses, we will be able to pinpoint those areas which are being affected by diseases. Then effect of phenology relates with the changing seasons. Now changing seasons affect vegetation by changing its appearance in terms of moisture content or in terms of aging of the tree or the vegetation. Then effect of canopy geometry. Uh, Vegetation may appear smooth, it may appear coarser depending upon the geometry. All those surfaces where vegetation is almost of same size, they will reflect a very smooth mm, smooth responses, whereas in case of for example forest cover, where we have different heights of trees, they will reflect the coarser reflectance values for vegetation. Then another important surface is the water. How do we identify various water surfaces? Now the reflectance behavior of water depends upon the reflectance of light energy, that is the visible spectrum. The depth of water plays a very important role, whether water body is deep or water body is shallow. Then we have suspended material, chlorophyll content in water bodies, and surface roughness. Now in the visible spectrum and near infrared, we see what happens is the incoming radiation, when it strikes the water body, okay, it will reflect various wavelengths in different proportion. Okay. So in this case, water bodies, they reflect maximum energy in the shortest wavelength, that is the blue band. Okay. Whereas green, red, and infrared, they are absorbed in higher proportion, and that is why any water body, it appears as blue or in different shades of blue to us, because it reflects maximum of the shortest wavelength in the visible spectrum, which is the blue wavelength, 0.4 micrometers to 0.5 micrometers. But then the depth, it plays very important role. If a water body is very deep, which means that this energy which will strike the water surface, it will not be able to reach to the bottom of the water body and then gets reflected back, which means that in that case, in case of deep water body, almost entire energy will be absorbed by water. So in that case, the reflectance will be very dark. Whereas in case of shallow water bodies, more energy will be reflected back, therefore it will appear in bright blue color. But then apart from that, we have suspended material. If water is clear, clear water will reflect the bright bluish shades. Whereas in case of water bodies which has high suspended material in it, it will absorb more of energy, and therefore its appearance will vary. Higher chlorophyll content, sometimes water bodies they also appear greenish to us, so that greenish color is due to the higher chlorophyll content in the water bodies. Okay, in that case, apart from blue, surface is also reflecting higher amount of green wavelength, 0.5 to zero point 0.6 micrometer energy, and therefore that water body will appear bright green to us. Surface roughness relates with the calmness of the water body. If water body is still, water is not moving, more of energy will be reflected. But in case of rough water bodies, if there are ripples, then instead of reflecting energy, water body will scatter more of energy, and its spectral response will vary. Okay. But always remember that spectral responses of any surface, whether it's vegetation or it's a water body, uh, uh, no single factor affects the reflectance behavior. All these factors they work in combination to produce the unique appearances of these surfaces on satellite images. Maybe sometimes one factor is more dominant, but nonetheless all the factors they work together. Now this is one example of the a comparison between the reflectance behavior of water and vegetation. See, so we have drawn these curves in visible spectrum to near infrared part, that is 0.4 micrometers to 0.8, 0.9 micrometers. So if we see that reflectance behavior of both water and vegetation, okay, they are very similar. Similarity is that both the surfaces they are reflecting very small insignificant amount of energy, so between 10 to 20 percent of the incoming radiation. So in this case you see at 0.4 and 0.5 micrometers it is difficult to differentiate between the two surfaces because the spectral curves they are almost same. The variation, the differences in the spectral responses are very less, whereas in case of 0.6 to 0.7 micrometers, although the reflectance of both the surfaces is about 10 to 15%, but then there is a gap, huge gap in their spectral responses, and therefore we can identify these surfaces at this wavelength. And particularly after 0.7 micrometers we can see that vegetation starts reflecting higher energy. Okay, the curve is moving upward, whereas in case of water the curve is moving downward. Okay, and at roughly about zero point 0.8 micrometers water is not reflecting any kind of energy. So which means that if we see water bodies in any wavelength beyond 0.8 micrometers, water bodies they will appear dark black, because in those wavelengths water will not be reflecting any kind of energy, whereas vegetation at 0.8 at 0.9 micrometer it will reflect higher amount of energy. So which means that if we have to differentiate, distinguish between water bodies and vegetation cover, use of near infrared 0.8 micrometers 0.9 micrometers wavelength are more useful in differentiating both the surfaces. Then snow, a large part of this earth is covered under snow. Usually for human eye snow appears white. Okay, and the reason snow appears white to us, that snow surfaces they reflect a very high amount of energy. Usually fresh snow it reflects 80 to 90% or even higher amount of energy that strikes the snow surfaces. Okay, and this is one of the reason why we are advised to wear sunglasses while going to a snow covered area, because the reflectance of snow is mm, very large, and because of this high amount of reflectance sometimes it can cause slow blindness. Therefore we require to wear sunglasses while traveling through snow surfaces. Now in case of snow, The factors that influence the spectral behavior, these are the grain size, the snowpack thickness, how thick the snow covered area is, the liquid water content, and the impurities. Now, grain size, as the grain size of snow increases, its reflectance decreases. Thicker the snow surfaces, again, it will reflect the less amount of energy. Thicker snow cover means that snow is deposited in that particular area for a very long period of time, and therefore its physical property has changed because of changing temperature conditions, or maybe due to changing pressure conditions, or maybe due to introduction of impurities in that surface. So thick snow cover, it will reflect less, whereas in case of thin fresh snow, it will reflect higher energy, and therefore it will appear very bright. Liquid water content, again, as due to the temperature and pressure, the liquid water content in snow cover will change. Higher liquid water content means that higher melting is taking place, and since water is a very good absorber of incoming radiation, it will absorb more energy. So higher water content in snow covered area, that surfaces will reflect a slightly lower amount of energy as compared to the fresh snow. Impurities refers to introduction of dust particles, rock surfaces, debris from the adjoining area to snow surfaces. So based on our understanding of these properties and their behavior, we can identify different snow cover areas. We can also identify areas where fresh snow is being deposited, and based on these reflectance behavior, we are able to demarcate snow covered area or changes in the snow cover in mountainous areas. Now, snow has a very typical way of interacting with the incoming radiation. In case of snow, snow surfaces, they do not have any bias towards reflection of at different wavelength, which means that within the visible spectrum, the snow cover reflects equal amount of energy in visible spectrum, that is in the blue band, green band, and red band. Okay, so the same principle is applied here of color composition. If we mix three primary colors in the same proportion, we end up with getting the white color, and because of the equal amount of reflection by snow surfaces, we see snow covered area as white. However, another important feature, that is cloud cover, they also appear white to us because they also reflect energy at different wavelength in equal proportion. Okay. So how to differentiate between these two surfaces? Okay. So in this case, in the visible spectrum, both cloud cover as well as the snow cover area, they will appear white in visible spectrum. So therefore, it is not a good idea to identify these surfaces in the visible spectrum. Okay. So but if we use different wavelengths, okay, so we'll find that the behavior of these two surfaces is different. Beyond near infrared part, both the surfaces have different spectral responses, and they can be identifiable. Then another important surface is the soil surface. Okay, like water bodies, snow covered area, okay, the reflectance behavior of soil is affected by moisture content, the amount of water present in the soil, the organic content, the texture of the soil, whether that soil is coarse or soil is firm, the structure of the soil, and the iron oxide content. Now, these are different spectral reflectivity curves for different surfaces. So we have all of these are representing the natural surfaces, we have spectral reflectivity curve for vegetation, we have spectral reflectivity curve for soil, for water, for snow cover, we have spectral reflectivity for cloud. Now these are the average response for these surfaces. Okay. And by comparing our satellite data with these average curves, we can identify and differentiate objects. So let us start with the vegetation curves. So we have two different curves for broadleaf vegetation and needle-leaf vegetation. Okay. Now broadleaf vegetation, usually in this case we are talking about the deciduous kind of vegetation, and needle leaves are the conifers. Okay. Now if you look at these two curves drawn in green color, you see it is very difficult to differentiate between broadleaf vegetation and needle leaf vegetation, because in case of visible spectrum, 0.4 to 0.7, roughly up to 0.8 micrometers, you see the curves for both the vegetation, they are coinciding. So which means that in case of visible spectrum, it is not possible to differentiate between broadleaf vegetation and needle leaf vegetation, because they will reflect in same proportion. But in case of near infrared part, 0.8 to roughly about 1 micrometer, you see there is a difference in the both curve. The needle leaf vegetation is reflecting about 70% of the energy, whereas in case of broadleaf we have about 80 to 85% of energy being reflected by the vegetation. So this narrow spectral width of near infrared, 0.8 to 0.1 micrometers, can be used to differentiate different vegetations, because even beyond 1 micrometer, you see again the spectral reflectivity curves for both the surfaces, they are coinciding. Okay, which means that again even at the longer wavelength, it is not possible to differentiate between different vegetation surfaces. So therefore again the near infrared part is more suitable for differentiating various vegetation surfaces. Another is the difference between different soil types. We have dry and wet soil. Okay, so you see wet soil means higher moisture content, and higher moisture content means that surface will absorb more of energy, because water will absorb more energy. So therefore its reflectance behavior will be less, whereas dry soils, they will appear bright. But again these are standard curves. It does not mean that every soil will reflect in the same proportion. Okay, but the curve, the orientation will remain the same. Okay, so in case of dry soil, for example, the sandy areas, desert areas, their reflectance, the curve will remain same, but the proportion of energy reflected will vary. Okay, so in case of desert, this reflectance could be more than 70%, 80%, or even 90%. Okay, so they will appear very bright, because in deserts will have deficiency of water. So in case of deficiency of water, the surfaces, they will not absorb energy, they will reflect most of the energy. In case of water bodies, you see water bodies cannot be identified beyond 1 micrometer. Okay, after near infrared part, water bodies will always be appearing black in satellite images. Okay. So you see the best spectral wavelength for identifying water is the visible spectrum only, because only in the visible spectrum water surfaces reflects about 30 to 35% of energy, and as the wavelength increases, the amount of energy reflected by water bodies, it starts decreasing, and beyond 1 micrometer, then there is no reflectance of any kind of water surfaces. Now most interesting part is the reflectance behavior of snow and ice. Okay. Both the surfaces, they are representing the same surface, that is water, but in different phases. In case of snow, we have snow and ice, we have the solid water, where in case of cloud we have vaporized water content. So in case of snow, ice and cloud, you see in the visible and near infrared part, both the surfaces, they are reflecting very high amount of energy, and that is why they are appearing very bright on on a visible or near infrared satellite images. Okay, but again it is very difficult to differentiate because the difference in their spectral responses are very small. Okay, but after zero 0.9 micrometers, you see cloud keep reflecting almost the same amount of energy, that is about 80 to 90% of energy, whereas in case of snow, see there is a decline in the reflectance behavior, which means that beyond near infrared part, snow and ice, it will start reflecting less and less amount of energy. And see, at roughly about 1.5 micrometers, we have about 20% of energy being reflected by snow surfaces. Okay. So for differentiating between a cloud cover and snow and ice sheet, so we use higher wavelengths. Okay, that is near infrared or the higher wavelength. So differentiating these two surfaces is easier in the higher wavelength regions. So now, depending upon these uh, characteristics of different surfaces, then we can relate our satellite images and the reflectance behavior in that satellite images, and then we can identify different surfaces, whether a particular surface is a water body, or it's a vegetation, or it's a settlement, or it's a cloud cover, or ice sheet, or any other surface. Now, these were the standardized procedures which we use to interpret the reflectance behavior. Okay, but now how actually this interpretation, extraction of information is done? Okay, there are certain elements which we take into consideration for analyzing various surfaces. So we have different orders of elements which are used for interpreting satellite images. So we have first order, or the most basic elements of image identification. These are known as the first order elements, and these includes tone. Tone refers to different shades of gray in case of black and white satellite images, or hue, that is the different shades of color, different colors, color combination. Another is the resolution. Okay, in this case, resolution is the spatial resolution, means finer details, smaller size pixel will give us the finer details, whereas the large size of the pixel, it will give us the lesser detail. So the first order element is the tone or hue, different shades of gray or different colors. Okay, now different shades of gray, they form the basis for identifying surfaces. You see these pictures, some of them we have already seen. In the first image, we can see there are different shades. There are certain areas, patches, which are reflecting very bright color, whereas there are some areas which are appearing darker. Okay, now using these differences in the tone or the hue, we are able to identify surfaces. For example, in the first picture, the bright surfaces, they are representing the bare surfaces, where these surfaces have least amount of moisture content, whereas the dark surfaces, either they are irrigated fields or some sort of vegetation is growing on these. Therefore, we have, for the same land, we have different tones, and depending upon the variation in the tone, we are able to identify the differences. The color is the most important element in identification. Identifying different shades of gray is very difficult, because the human eyes, we are not trained to see different shades of gray. Okay, we can only identify, let's say, about 5 to 10 different shades of gray between pure black to pure white. If we have more than, let's say, 50 or 100 shades of gray, after a certain point we will not be able to make the difference between two shades of gray. But in case of colors, our eyes are more trained. We can identify higher levels of colors. Okay, different colors we can more easily identify. Therefore, color play a very important role. Just by looking at the color, sometimes we get to know what kind of feature we are dealing with. Okay, for example, the blue color, different shades of blue will instantaneously tells us that we are looking at some water body. So we can make greater detailed analysis further, but at the first instance, just by looking at the colors, we can identify various objects. Another is the resolution. Again, the size of the pixel. Smaller the size of the pixel, better will be the resolution. So in these three images, we have three different resolutions. The topmost image, we have the large size pixel, which means that one pixel is covering a very large area, and therefore resolution is very coarser. Whereas in the third image, we have very small size of pixel, and we are able to identify surfaces which are very small. So as the resolution of satellite images it increases, our capability of differentiating surfaces it also increases. Then the size of the object itself. Okay, now size is very important. By comparing relative size of the surfaces, we are able to identify those surfaces. Okay, for example, if we are seeing some buildings, just by looking at the size, we are able to identify whether that building is a house or that building is some another. So all the institutional areas, the buildings are of bigger size. Okay, whereas the residential area buildings are of the smaller size. So just by looking at the size of the surface, we are able to identify what kind of surface it could be. Then we have shape, the shape of the object. So in this case, we have depicted two different surfaces. The first picture, topmost picture, it is representing a mesh of flyovers, roads. Okay, so by looking at the orientation, the linear orientation, okay, we can see that it's some sort of a road, and just the shape tells us that these are representing group of various flyovers. In the lower picture, we are seeing the circular kind of shapes. Okay, now the smoothness of the surfaces, it tells us that we are looking at the agricultural field. The reflectance, the shades are very smooth, but the circular size of these fields, because we usually do not see agricultural field in such shape. Now these circular shapes, they are representing fields which has sprinklers installed in. So depending upon the movement of sprinkler and the variation introduced by the irrigation activities, we have the circular shapes of. So shape is another important factor. Okay, then texture, whether that image is looking smooth or it is looking coarser, it gives us the idea about the surfaces. Any land which has the uniform land use, okay, for example a water body or a desert or a playground, the reflectance will be very smooth. Whereas in case of those surfaces where there is striking differences in the surfaces within smaller distances, the area it will appear coarser to us. Okay, so texture is another important characteristics for identifying these surfaces. Pattern, the geometric arrangement of the surfaces, is another important factor. So in the first picture, you see we can see a very geometrical arrangement of objects. In this case, these are representing trees. Now, in case of vegetation that has a geometric arrangement, it represents some sort of plantation or orchards. Whereas in case of forest cover, we don't find any kind of linear arrangement or any kind of pattern. Okay, so in this way we can identify surfaces, whether those surfaces are natural surfaces or these are man-made surfaces. Okay, same is the case with the lower picture. Here we can see the arrangements of different buildings. Okay, so by just looking at the arrangement, we can see that it's some sort of a planned settlement. We can identify that. Okay, because things are arranged in a geometrical form. Okay, then site refers to how an objects are arranged with respect to another surfaces. Okay, so sometimes identifying one surface is dependent on identification of some another object, and by identifying those objects we can then identify the surfaces also. Okay, then associations takes into account the relationship between the other recognizable objects or feature in proximity to the target or interest area. For example, a school is always associated with the playground. Okay, so if on a satellite image we see a very large building along with a playground, okay, we can associate these two surfaces together, and then we can say that this particular area is representing some sort of institution, maybe a school or a college, okay, or a sports complex. Okay. So by establishing these association, we can identify various surfaces. But again, these surfaces, these different elements of image interpretation, they are not applied individually. We use all these elements together to interpret the satellite images and extract the information from these satellite images. Another is the last important factor is the height. Okay, now height can act as a aid to image interpretation. It can also hamper our capability of identifying objects, because as a particular surface has a particular height, it also casts shadow. So therefore, for example, a very tall building, okay, it will also have a shadow, and all those areas where that shadow is being casted, they will appear very dark. So we will not be able to identify or recognize any object from those areas where we have shadow. Okay. But at the same time, that shadow will help us in identifying the height of the surface. Okay. So by looking at the shadow, and since satellite images, they are captured on a particular scale, so using that scale, we can identify the height of the objects also. So which means that using this shadow, we can also quantify the surfaces. So we can identify different buildings. We can differentiate between a house and an industry. We can also calculate the rise or the height of tall buildings. Okay. So using these elements of image interpretation, we can extract the huge amount of data from satellite images, but the extraction of data is dependent upon the purpose of our analysis. Okay. Secondly, it also depends upon the expertise. Okay. So any expert using these basics for image interpretation can identify, extract the information pertaining to his or her field. Okay. For agricultural scientists, they will extract information pertaining to agricultural land use or any kind of such analysis, whereas a geographer will be more interested in say for identifying settlements, identifying the types of settlements, or maybe some sort of terrain analysis can be done using information extracted from these satellite images. So with this, I finish the lecture on the interpretation. If you have any queries, we can discuss, we can take your questions.